In this problem, we ask what horizontal force will hold a 50 kilogram mass stationary on a frictionless plane at an angle of 35 degrees. Let's think about this for a second. There's going to be a weight component down the incline, a weight component parallel to the incline, a normal force in response to the weight component, and also in response to the component of the force that's perpendicular to the incline. The force will have a component perpendicular to the incline and a force parallel to the incline. Okay, there'll be, well, we'll see in a minute. The normal force will be a response to both that perpendicular component of force and the perpendicular component of the weight of the object. The horizontal component, or the x component of the force, the parallel component, the component parallel to the plane, will be equal and opposite to the weight component down the incline. If we start the problem by simply sketching a force diagram, first of all, in black, we have the horizontal force that we're applying, the weight force, and the normal force in this direction. These aren't necessarily to scale, they're just drawn any old way. We're going to put an x-axis here parallel to the plane and a y-axis here, and that's going to of course be perpendicular to the plane and parallel to the normal force. Now, as we usually do, we're going to break the weight into its x and y components. The component parallel to the plane, which is of course the component that tends to accelerate the object down the plane, and the component perpendicular. And we're going to do the same thing with this force. We're going to have a y component of the force and an x component. The x component will be parallel to the plane, the y component perpendicular. Now we're going to want to adjust this force in order to make this x force equal and opposite to this weight force. And the normal force will arise in response to, again, to the Fy and the Wy components of the force and the weight. If we move up here, we see the four components. Things are a little crowded here, but let's see what the labeling looks like. The x component of the force is going to be F times the cosine of 325 degrees. If we go back and, well, if we think about it, a horizontal force, a force coming out in this direction, is going to be on an incline of 35 degrees. We're going to have 35 degrees between the horizontal and the x-axis. So this force will be 35 degrees below the positive x-axis. That's at 360 minus 35, or 325 degrees. The y component of the force will of course be the force, magnitude of the force, times the sine of that angle. The weight is in this direction, and that's 35 degrees back from the positive, or from the negative y-axis. And 35 degrees back from the negative y-axis is 35 from 270, or 235 degrees. So the y component of the weight is 490 newtons times the cosine of 235 degrees. The x component is of course 490 newtons times the sine of 235 degrees. The normal force is just there. We haven't labeled it. It has only a y component, and we'll find out what that is shortly. Okay, here we simply note that the force is at 325 degrees and the weight is 490 newtons at 235 degrees. Now we list all of the x and y forces. Let's adjust ourselves to get parallel to the camera. Okay. The x component of the force F turns out to be 0.82 F. The 0.82 is no mystery. That's just your cosine of 325 degrees. The negative 0.68 F is just the sine of 325 degrees. There's your negative 0.68 times F. The weight components, when we do the cosine and sine of the 235 degrees, we're going to end up with an x component of about negative 300 newtons and a y component of about negative 400. Now these are just approximate. You can rework this and get the precise values if you really want them. But here we're just trying to illustrate. Okay? And the normal force has 0 x component. The y component is just the magnitude of the force itself. So that the total of the x components is 0.82 F minus 300 newtons. The total of the y components is negative 0.68 F minus 400 newtons plus the magnitude of the normal force, which we have written right here. Writing out the forces in the simplified form, we have 0.82 F here, negative 300 newtons here, negative 0.68 F here, negative 400 newtons here, and the normal force here. Now the sum of the x forces is 0, and that tells us that the expression that we got on the previous page, or what we can read off of this, tells us that the 0.82 F minus 300 newtons is 0. We can solve this for F very easily, and we get 366 newtons. So we found the horizontal force, and that's really the end of the problem as stated. But since we're here, we might as well go on and illustrate how we find the normal force, and that's pretty easy. Once we found that this force is 366 newtons, we can plug in 366 newtons here and get this force, and then the normal force will be equal and opposite to the sum of these two. We get that formally from the condition of y equilibrium. The magnitude of the normal force minus 0.68 F minus 400 newtons is 0, so the magnitude of the normal force is this plus this. Put our 366 newtons in here, and we get the magnitude of the normal force. We'll add if there was some frictional force, of course it would be some multiple of the normal force, but if there's friction, that would change this whole problem anyhow.